Good afternoon. This session is how to industrialize your data platform with Google Cloud Platform and open source technology. I'm Jason Clark. I've been with Monsanto/Bayer for a little over 9 years now. So to start with, who here has seen an ear of corn up close and personal? If you have, you've probably noticed that on that individual ear of corn, there are a lot of individual kernels. Right? On an ear of corn, you can have anywhere between 800 and 1,200 kernels on that single ear. Each of those kernels has a lot of information packed inside, a lot of information that's very useful to us within Bayer Crop Science in making decisions on how we drive our product pipeline. And what I want to talk to you today is essentially asking the question, like, what if we could take all that data that's packed inside each of those kernels that are on those ears that are in these fields where there's thousands of corn plants. What if we could take each data about each of those kernels and engineer an information pipeline that can help us mass produce knowledge about our product pipeline and ultimately make more informed decisions that help drive useful products to market that can aid in producing more bountiful harvests. What I want to convince you of is that we have, as an engineering team, produced an information pipeline that leverages historic observations, crop data that we have to further characterize our products and ultimately improve decision making, but at a fraction of the cost that we would incur to have done it previously. So let's take a step back here. I'm with Bayer AG. I'm actually part of Bayer Crop Science, and when we look at our product pipeline for Bayer Crop Science, it really comes down to 3 high-level steps. Number 1, we're going to try to identify market needs, right? What treatments can we pair with seeds and genetic characteristics that we know about our corn plants, as an example? How can we pair these things together and produce a product that ultimately improves yield for our farmer customers? Once we've identified what those market needs are, we'll start to actually develop those product concepts. Step 2, when we're developing those, what we're ultimately doing is, over the course of years, taking each one of those seeds, planting them, pollinating them, harvesting them, and starting that whole cycle over, shipping seed around the globe, and performing that cycle year over year. And while we're planting and harvesting these things, in between there, we're measuring a lot of data and recording a lot of data about those seeds. Fundamentally, there are two data sets that our team cares about that contribute to driving that product pipeline. Genetic data, which would include genomics, and phenotypic data. So genetic data being, what do we know about the genetic makeup, the genome of these seeds that we're moving through our product pipeline. And phenotypic data being, what can we actually observe? Is this ear of corn yellow or is it white, right? That's a very simple characteristic, but you can imagine much more complex characteristics that we're measuring as well. And then ultimately, once we've identified that product concept, we've developed this product concept, we're sure it's the right fit for our customers, we'll commercialize it. At each of these steps along the way, there are different elements of our data stack that are important. And what I want to do today is tell you who we are as an engineering team, and then tell you how we've applied some principles to industrialize our platform and allow for large scale across our consumers and within our platform to ultimately produce knowledge. So who are we? How do I fit into this picture? I work for a really strong engineering team called Product 360 within our data landscape. What we do is we engineer a versatile, enterprise-wide data asset platform that's really core to other business layers. What does that mean? Well, fundamentally what we do is we provide access to core product data sets in various ways, various modes of access across various personas. So everything from other software products that are being built within the company to data scientists that are trying to identify what those next product concepts could be, all the way up to our domain experts, the people working in the labs, the people that are really doing the hands-on work to measure and observe characteristics about these seeds that are moving through our pipeline. Now, what that means is that with that variety of consumers and spanning that long of a pipeline, again, the course of years, we really build up some demand in terms of usage of the platform that we built. To kind of give you a sense for that usage, API requests. So again, the fundamental mode of access for the data sets that our team delivers is through APIs, and we'll get into kind of the different modes of access for those APIs in just a few moments. But what you can see here is, on average, monthly, over the course of the last year, we've had 323 million API requests. So we're not talking internet scale, but we're talking pretty sizable usage for when you consider that all these consumers are within our company. Now, another thing that you can see here is peak usage. And what you can see is that agriculture is fundamentally a seasonal business, right? We'll see spikes in usage at various times throughout the year. We've seen one month where we've had 1.16 billion API requests across our platform. So who are those coming from? Well, we measure that as well, and we'll talk a little bit later on about how we measure this data. Active applications. So application being considered, a software product that's using our platform in some way, an analytical model that's using our platform in some way, also inclusive of individual data scientists that may be using our platform in some way. We've seen an average of 85 active applications per month, spiking up to, again, 116 with those seasonal workloads. Now, our platform is not stagnant. It's not stale. It's changing every day. We release, on average, 23 times a month to production, with a peak in there of releasing more than one time a day. Now, we're not releasing hundreds of times a day. We don't have that need. But what it does show is that our platform is still evolving. And some of the principles that I'm going to talk to you about help us give us that wiggle room to continue to evolve the platform as we continue to expand the usage and provide value for our consumers, produce new knowledge for the organization. To kind of give you a sense of the breadth of the platform, we're looking at about 40, a little over 40 resource collections. All those data sets, those resources, are all different shapes and sizes. Some may be graph structured data, some may be traditional relational data. They're all different, but they all fit into the puzzle in some way. And we don't just distribute our databases, we distribute our engineering team as well. We've got a team of 30+ data engineers, split into 5 to 7 person teams, focused on different vertical areas within Product 360. So with demand like that, how do we go about building a platform that we can scale, that we can use, that our consumers can use, and our consumers can scale? To do that, we've had to develop some basic principles. And if we think about this like we're designing a factory of knowledge here, and we're trying to lay out our factory floor, what are some of the principles in designing that factory floor that we've tried to follow? Well, number one is we want to minimize retooling, right? We don't want to have to reconfigure that factory floor and incur downtime in that production of knowledge if we don't have to. We want to minimize that. Number two is we want standardization, and we want each component on that factory floor, we want its job and its purpose in life to be obvious, right? We want somebody to be able to look at that layout and say, I know why this piece is here. But we also want that indirection as an engineering team to be able to swap a new component in that does that job at least a little bit better if necessary, right? So we want that ability to refactor, but we don't want to cause our consumers to have to retool. The next thing is if our factory floor stops working, we're no good for our consumers. We're not producing knowledge. We need a really clear view of the health of our factory floor, right? We need key performance indicators that can tell us how that factory floor is operating and where the bottlenecks are at, right? Where are we introducing bottlenecks into this process of producing knowledge? So I want to walk you through, in the next few slides, how we apply some of these principles and how we design for them. And then what I want to do is come back and make it more real. So we'll talk kind of about in an abstract way about those principles over the next few slides, and then we'll bring it back and we'll talk through a real use case and show how we've applied those principles in a real information pipeline. So let's start with standardization, right? We want those components to easily be swapped in and out, but we want their purpose to be obvious. That comes back to me to readability and flexibility. Those two things. So let's start with readability. If we think about readability from a code perspective, what does that mean? It means fundamentally my code base is more maintainable because someone else can come in and understand what that software is intending to do. We want our data model to operate the same way. We want our consumers to be able to come in, look at one resource, get familiar and comfortable with that resource, and then when they go to use another resource, not have to worry about reconfiguring their mental model. We want it to look similar. We want our resources to look similar such that they can jump across those resources with a minimal amount of friction and really combine data together to produce new information for the company. Standardization is how we get there. And the way we've standardized is by adopting Google's resource-oriented design guidelines. If you've ever used the Google Cloud APIs, this will feel familiar to you. This is a lot of the principles that are applied in the Google Cloud APIs. And you'll see some things show up here in a few moments directly out of those design guidelines. One thing that really cemented for me putting importance in API design was Martin Nally's talk last year at Cloud Next called Designing Quality APIs. It's a really good watch if you're interested in API design and why it's important and how to go about it. It's a really good watch and a really good place to start. Now, we talked about readability. Standardization is helping give us that readability, and it's helping give us that ability to swap in new components as an engineering team. But what about flexibility? If we're so rigid that we have to change our APIs every time a new attribute's introduced into a business workflow, that maybe something's hyper-specific to that workflow, well, that's going to be retooling for us, and it's going to be potentially retooling for our consumers by way of a breaking change to our APIs or a new version of an API that they have to rapidly adopt, right? It's going to cause churn, it's going to potentially cause downtime and loss of productivity. So what we've done is we've adopted a concept from the resource-oriented design guidelines, and with these guidelines, we try to not be dogmatic, we try to be pragmatic. So we'll start with the resource-oriented design guidelines, use that as our base, and then if there's something that maybe makes more sense because we have more context about our development workflow or our customers' workflows, we'll adapt it and we'll make it fit that. But we use the resource-oriented design guidelines as our base. Resource annotations are an example of that. There's a concept in resource-oriented design called labels. And if you've used the Google Cloud APIs, again, you've seen this concept, or really any cloud API, you've seen this concept in some way. It's essentially bring your own context, right? I don't have to tell Google Cloud, hey, can you add this attribute to the Compute Engine API so that I can capture it? I can add that, and it's specific to me, and it's relevant to me, it's understandable to me. We've adopted that same principle with our API design. We've got a lot of workflows internally that spin up and spin down quickly, right? We want to be that base. We don't want to have to change our APIs and introduce downtime with every change to the business workflow. So this enables that bring your own context. An example here is that this is really just key value pair data, right? So we've got some base schema that is giving you a definition of the kind of core enterprise attributes for that particular resource, and then you've got annotations that you can apply on top of that resource to bring your own context. An example would be, if I wanted to label a particular seed as being part of a drought initiative, I could add that annotation by way of a key value pair. And in some cases, we do have controlled vocabulary implemented over some of those annotations, but mostly it's free form. It's meant to be a piece of flexibility for our consumers. Another way that we enable flexibility is through this concept of resource sets. So we've got resource collections that we expose as APIs. And then, I think what we've seen a lot of is that people like their things and they like their groups of things. They want to bring context by way of taxonomically organizing that data in some way that's meaningful and relevant to them. Resource sets give us that. It's another resource. It's structured as a resource, standard API, but it gives you the ability to group a particular resource by way of filter values, right? So let's say I wanted to keep a list of all the products that are moving through the pipeline for 2019. If I have a products resource and a product sets resource, I can do that. I can provide filter parameters, and I can either manually update that thing, or we're moving more towards this concept of dynamic sets, which is basically filter parameters with context, right? So give it a name that thing, and then it can be reused across the organization. It's a way to deduplicate that data, but also give our consumers some control and some flexibility in the management of that data. The other side here is that we don't want to impose trade-offs on our consumers where we don't have to. We want to push the ability to make trade-offs back into their control. There are a couple ways that we do that. So I've talked in generality about resource APIs, right? Resource just being a particular data set. We provide multiple modes of access to each of those data sets. One is gRPC. So we've wholesale adopted gRPC across our platform as a mode of access for each data set. We've also enabled REST. We see definitely more usage on the REST side from less technical consumers, people like data scientists, people that aren't programmers but are trying to get their job done and need to interact with these APIs to access these data sets. REST is going to work with more out-of-the-box tooling and just be an easier experience, but gRPC is going to give you that performance. We've done some head-to-head benchmarks of REST versus gRPC, and there's definitely noticeable performance gain there with gRPC, but as a consumer, as a data scientist, I don't want to have a high barrier to entry for accessing these things, so we provide both of these modes of access. The kicker here is that if I want to string together multiple resources to really make something meaningful, that can be more difficult, right? I have to be somewhat of a programmer to be able to do that, to call these APIs, do some sort of transformation, pipe that into another API, do transformation off of that. How do we make it easy for consumers to join this data together? That's where GraphQL comes in for us. So we've got a GraphQL server that, again, can be used by any of our consumer personas, bench scientists, data scientists, enterprise application. They can use this GraphQL server, which in turn calls our gRPC APIs, right? So we get the performance of calling gRPC APIs, but we can do a prescriptive join of that data for the consumers. This gives, again, the consumer the ability to trade off who's doing the join, right? If they have more knowledge potentially about a better way to pre-filter data and join that with another data set, they can do that. They can do that by way of gRPC or REST. They have that ability. If they don't want to join that data together manually, they don't have to. They can call GraphQL, our GraphQL API, and we'll do that join for them. Both of those are synchronous modes of access, right? Request response for our consumers. The third pattern here that we follow is we've adopted Cloud Native Computing Foundation's Cloud Event spec to publish an event stream for each of our resources. That event stream notifies on standard create, update, delete operations, right? It can give our consumers a hook into our ecosystem to react asynchronously to events, goings on in our ecosystem. This again gives our consumers a way to decide what model fits their particular workflow, whether that's an enterprise application that wants to react as new enterprise data elements are created, or a data scientist that is really just trying to get these data sets combined together and move on with their lives so they can do really focused on their job, their core responsibilities. That's heavily focused on the consumer side, right? As an engineering team, we also try to take that idea of standardization and use that as our indirection to the back end. And that gives us the ability to use data structure as a competitive advantage. So again, I mentioned that we've got 40 plus resource collections. They're all different shapes and sizes. We've got data sets like our pedigree ancestry data set that tracks seed lineage, right? If we think about that corn kernel, we plant that, we pollinate it in some way, we harvest new seed, and those seeds are linked together genetically, right? One came from the other. And we do that over the course of years, sometimes multiple times a year for that particular line of seed. That produces a lot of data, and that data is naturally structured as a graph. And with that data set, what you see on the right-hand side here of the slide is an image that my colleague Tim Williamson tweeted a while back that is actually a representation of our ancestry data set for corn. Each of those stars in this galaxy are corn seeds, and the links between them are genetic relationships. These seeds came from these seeds, right? It gives you a sense of the scale of that data set. This is just corn. Now we work in a lot more crops than just corn. If this is interesting to you, I would highly encourage that you go out and look and watch Tim's presentation from Graph Connect a couple years ago. He goes more in depth in how we've modeled data in Neo4j for that pedigree data. But the point here is that we can specialize from an engineering perspective, right? We have that indirection. None of this is novel, but that standardization gives us a good way to kind of plug and play. We can start with a relational database for a data set like this if we wanted to, and then optimize the back end later. And with minimal friction, or ideally no friction for our consumers. The other side of our data footprint is Cloud Spanner has rapidly become our primary database. So we're coming from a legacy environment with a large Oracle instance that was really good at its job for what we needed at the time. As we've moved to a more of a microservice model, something like Cloud Spanner has actually become very, very useful for us. We've made smaller, thinner, more well-defined resources, so we're not trying to facilitate 7 table joins to get data back. Cloud Spanner has been a really good fit as well because, again, different data sets of different shapes and sizes, size being the key word in that. We have a few data sets that are very, very large, and those are the data sets that we'll actually talk through in our real-life example. To give you a sense of the scale of our Spanner footprint, right now we're at about 17 terabytes across our 2 environments. About 10 terabytes in our production environment, and the other 7 in our non-production environment. And our instance size floats between 10 and 50 nodes. Now that can get expensive, but we'll talk a little bit later about how we try to control that cost without sacrificing performance with Spanner specifically. So we talked a lot about getting data out of our platform. Let's talk about how we get data into our platform. Our most basic pattern for getting data into our platform is essentially data generator calling a resource API by way of gRPC or REST, right? Again, nothing novel. But there are some things, some characteristics about that particular workflow that are important. One, it pushes resource validation closer to the data generator. So if the data generator gives us bad data, that is synchronous. We can immediately reject that data and give that data generator context as to why that data is invalid. It keeps muck out of our enterprise systems, right? And it also prevents us as an engineering team from having to get in the muck if bad data is generated. The other characteristic is that the consistency model follows that of the resource API. So again, Cloud Spanner is essentially our primary database at this point. With the global consistency model, we can provide that same capability to our consumers. The flip side of that, the trade-off here, is that the data generator is sensitive to the performance of the resource API. If our resource API is slow and we don't have alarm bells sounding from our KPIs, that data generator is going to slow down, or they're going to have to deal with that in some way. They're going to have to engineer complexity into their system to accommodate that. So in cases where either it's not feasible for us to make something hyper-performant, or cases where that write is just high enough latency that it impacts the data generator and slows their work down, this pattern may not fit. There's another pattern where that pattern works well with kind of this new world that we're building, where we're building new workflows out in the cloud and engineering systems to bring us into a new landscape. The another right pattern that we have, though, is we do have, again, large legacy systems that have collected data over the course of 20 to 30 years. That data is still important. We still use that data to make a lot of decisions in our business because we want to look at that data over time. The way we get our legacy data into our systems in most cases is through a product that we have internally called the Enterprise Data Hub. What the Enterprise Data Hub is a set of replicated Kafka clusters that is managed by a central engineering team within our company. That product takes care of bidirectional replication between our different cloud environments, right? So we have a Kafka cluster on-prem, we have a Kafka cluster in AWS, we have a Kafka cluster in GCP. And Data Hub takes care of moving that data in and out of those environments for us. On the front end of that, we have change data capture mechanisms by Informatica Data Replicator in the case of SAP, and Oracle Golden Gate in the case of our Oracle environment. Those are pushing change capture records out. Those change capture records are making their way to Golang Kafka consumers that we have running out in Google Cloud, and still pushing things in through our resource API. So we're dogfooding those resource APIs even in this context. We're not ever making direct writes around the API to our databases, which again, hardens our workflows, right? If we're dogfooding it, we're going to harden that workflow much quicker than waiting for our consumers to find issues. And two, it's given us some of the same benefit. We can leverage those flexibility concepts as well and adapt our workflows very much quicker. One thing I would stress here too is that if you're interested in learning more about how our Data Hub environment is set up, former colleague Bob Lehman speaks to that approach from Kafka Summit last year. This is another really good watch that goes more in depth into our Data Hub setup. So that particular change pattern is generally lightweight events, right? The change capture records are, maybe 10, 15 columns, not big. And a lot of those can be kind of treated in isolation. However, we have a set of workflows, particularly in the genomics world, where we've got a lot of data that comes from a single event. So we have a single change capture record that comes across. That single change record can lead to creation of thousands of resources, all of which are fairly heavyweight. There's some meat to each of those individual resources. To accommodate that workflow, Kafka really doesn't encourage you to put super large messages on a topic in a partition. So to accommodate that workflow, we still stream out that lightweight event. We transform that lightweight event by joining it back to the legacy system and exchanging that lightweight event for those n number of large resources. We take each of those resources and we sync them as objects in Google Cloud Storage. When we do that, we rely on bucket notifications to publish out the other side, right? That's our change capture mechanism on the other side of cloud storage. So that bucket notification fires, we do, in some cases, a little more manipulation and massaging to that data, and then again, write it in through the resource API. So similar approach, but we're accommodating that large transformation that has to happen in the middle there. And we're doing that with GCS and PubSub. One of the things that we get out of this particular workflow is that with our Kafka workflows, we can't arbitrarily scale our consumption, right? Scaling of a Kafka consumer is bound by the number of partitions that you have, and repartitioning is generally not a pleasant exercise. PubSub gives us the ability to arbitrarily scale here. We have a single event that is infrequent that comes across, and we exchange that for a larger amount of information, and then we want to parallelize really wide to consume that information into our resource APIs as rapidly as possible. PubSub gives us that ability. We can scale out much, much wider with a button push, essentially with a change in a Kubernetes deployment size, a replicate count. So that's one of the benefits that we get out of this particular workflow as well. We don't always have control of our legacy system. And by control, I mean the ability to go back and exchange information with it directly. An example of that for us is SAP. So we don't ever touch our SAP environment by querying it, but we do have change data capture that's generated out of our SAP system. To accommodate that, we've actually paired Kafka and those change capture records with Spanner and Dataflow. So this is kind of more of the traditional replicate the data as is. We replicate as is into Spanner, so you'll see tables that look like SAP tables in Cloud Spanner. And then we use Cloud Dataflow to kind of give us this concept of a materialized view, right? We've got Cloud Dataflow running periodically as a scheduled job, taking data out of Cloud Spanner, making it into the format that we want to make it into to make it a more descriptive resource for our consumers, storing that data back in Cloud Spanner, and then our resource APIs are built on top of that. So it's essentially a cache, right? One of the things that we get out of using Cloud Dataflow here, we're heavily using Cloud Dataflow Java, but one of the things we get out of that is testable business logic, right? We can test those data transformations that we're doing. Whereas if we're building, traditionally building a 1,000-line SQL statement to build a materialized view, unit testing that is really hard and error prone and all these other things that make it really difficult to ensure we're not introducing breaking changes. With Dataflow and with Java, obviously, we can unit test in a similar way that we would any of our other software. Another aspect of Dataflow that becomes important here is that we can scale that as our data set size scales, we can increase our worker count. Again, it's a button push. So that gives us the ability to ingest a lot more data, if need be, without a lot of operational overhead or having to retool our environment. The trade-off here with this workflow is that this is not near real time. These other workflows that we've looked at are near real time. Moments after that data is written to the legacy system, it'll be available in our resource APIs for consumption by our consumers. This is not. This is scheduled. So this is, every few hours we run these transformations. We can squeeze that down and make it, a shorter frequency. We haven't had the need to do that, but it does suffer from this particular aspect. What you see on the right is an example of one of our simple data flow jobs. So when I talk about testability, this is kind of showing you, this is a simple job. Testing these things is important. So we talked a little bit earlier about how it's important for us to have key performance indicators, a view of our factory floor, right? We don't want to ever stop that production of knowledge. We want that to be available 24/7. So now I want to talk a little bit about some of the reliability engineering aspects that we've introduced into our stack. The most basic, but also one of the most useful, has been instrumenting our APIs to capture access log data, API request data. This captures essentially the who, the what, the when, and the how long for each of the API requests that come into our platform. This gives us a sense of how those requests or those APIs are operating for our consumers, right? If it's something slow, we surface this data through BigQuery, written through PubSub. So each API hands off the request to PubSub. We've got a process that syncs that into BigQuery, and then we surface it for our engineering teams using Data Studio. So it kind of gives you that end-to-end experience and gives our engineering team a view of that factory floor, but of their specific segment of that factory floor. Another aspect, you've seen how many of our data ingress patterns rely on Kafka. What we've done is create essentially a monitor for Kafka. That's not novel, right? But what we did in this case is use Kubernetes CRDs, custom resource definitions, to allow our engineering team to define their monitoring requirements for their Kafka consumers at deployment time. So instead of having to deploy my Kafka consumer, and then go somewhere else to say, here's how I should be alerted for this thing, you can push that information close to the deployment. This is a place where, to me, Kubernetes really, really shines. This extensibility allows us to describe our deployment workflow in the terms that we use and make it discoverable for our engineers, all through the surface that they're interacting with to do their application development daily. That alerts to Slack, push the messages close to where the engineers are. But it's a set of really simple Go processes that are watching for that custom resource definition to change. And last but not least, we've talked a lot about Spanner, and I mentioned that if we're running a large Spanner instance, that can get expensive. We also don't want to run a small Spanner instance and have that seasonal workload spike on us all of a sudden, and our API performance goes down the drain, right? We want stability, but we also want cost control. So we've written a simple autoscaler component for Cloud Spanner that runs in Kubernetes, uses the Stackdriver API to watch for CPU utilization numbers, right? It watches that time series and scales Cloud Spanner up and down using the Spanner API as needed. We've seen this drastically reduce our Spanner bill because we were over-allocating before to guard against poor performance if we saturated the instance. But we've seen now that CPU utilization with this autoscaler component hover between 30 and 50% utilization. So, we want to be using as much of that capacity as we can. We can't put those CPU cycles in the bank and save them for later. We're getting what we pay for at that point in time. This has been a big addition in terms of operations. Again, hands off for our engineering team. This autoscaler can take action. There's a little bit of risk in that the Stackdriver API is a minute behind. So if we see a real sudden burst, we may see a few failed requests. But overall, over time, it helps keep our SLOs in check. So let's make this real. Let's talk a little bit about one of the concepts that we've implemented on our platform, this information pipeline that we've implemented on our platform over the course of the last year. What we're doing is we're doing a process called Genotype Inference. So think about that corn seed again, that kernel. Again, each kernel is dense in information. What we want is a picture in a window into the information inside that kernel. Genetic markers give us that information about the genome of that particular corn seed, right? So genome being all the different nucleotide bases that compose that kernel genetically. Genetic marker giving some measurement at particular locations on the genome. And those locations are picked very strategically, right? We're looking for things that ultimately we know this marker or these set of markers lead to this this kernel being white or yellow, right? Things that we can observe that have meaning and value for our customers. The way we make those observations, we have two different levels of resolution. In red, you see low density resolution. What that is a smaller number of genetic markers that we capture spread across the genome. In yellow, you see high density observations. It's a lot more markers. It's also a lot more expensive to collect, right? So these are things where we're actually sending seeds to the lab and we're running experiments to get a window into the genome of these corn seeds. Now, if we want to capture low density observations, it's cheaper, it's easier, can be done more quickly, but it still costs a lot of money. It still costs money, right? And it's not just the money of running that experiment, it's all the shipping costs and all that comes into play to move seed to actually make those measurements. What we've done is we've leveraged mathematics, essentially, and programming, and these technologies that you've seen me talk about to infer these genotypes, which is at a much cheaper cost. We can basically take the data that we've measured, those two different levels of resolution, and we can fill in the gaps. We can upsample the low density resolution to a high density resolution, high resolution. And we can fill in those middle areas where maybe we didn't collect any data at all, but we know genetically this seed came from this seed came from this seed. And genetics gives us certain rules that we can put into play and make estimations about what the genome of that particular seed in the middle, of which we made no direct observations, actually looks like. We get a probabilistic value that allows, again, our consumers to make the choice of how confident they want to be about that picture of the genome, right? Again, allowing the consumer to make more decisions. To give you a sense of how much data we've generated with this information pipeline, what you see, again, in yellow is the high-density observations. So we collected a lot of information, a lot of markers, on a smaller number of seeds. With the low-density observations, we've collected a lot fewer markers. We've observed a lot fewer markers, but we've done it on a larger number of seeds. The blue is the area that we filled in. I talked to a colleague this morning just to make sure that my number was right on that number, or on that blue area. We're talking about 197 billion genotypes that we were able to generate and infer from those data sets. This is something that was previously unachievable, and we've done it at a much lower cost. And we've done it this way. So let's walk through this diagram real quick. This is our architecture for this genotype inference pipeline. Let's talk about some of those principles that we laid out earlier. So if you go left to right, starting from the bottom, we've got a lab workflow, a lab system that's pushing data in to our observed genotypes resource. That's backed by Cloud Spanner. All of that data is in Cloud Spanner. From there, you get a Cloud event. You get that asynchronous notification that new data has arrived. There's a component called the orchestrator that's listening for those events and then scheduling these inference jobs. And it's doing that on Kubernetes by way of GKE as pub/sub messages that get distributed across multiple regions, multiple Kubernetes clusters in multiple regions. And those pods, their sole purpose in life is to do that calculation for us. To do that calculation, to infer these genotypes, they'll reach back in to our resource APIs to grab those observed genotypes. When they complete their purpose, they'll write that new data set out as an inferred genotype into our inferred genotype resource. One interesting thing about that, one of the Spanner talks that we were in earlier this morning, they talked about using Spanner for GCS metadata. Similar approach here. We store the metadata for these data sets in Spanner so that we can more rapidly search over it, but the bulk of the data, the payload for that, is stored in GCS because it is large. We're talking 85,000 genotypes for a single seed, right? And then we're talking millions of seeds that we're inferring these genotypes for. So that data set grows rapidly. A few interesting characteristics to facilitate this workflow. The workers actually run on preemptible VMs. So that's actually been a huge mechanism for us to control costs in this process. Preemptible VMs, you get at a fraction of the cost of a normal VM, but you get that resource, those compute resources for a limited amount of time. To engineer for resilience to preemption, we've done a couple of things. One is checkpointing. So we checkpoint intermediate state out to GCS as these workers run, so that if they do get preempted, they can pick back up from where they left off. These jobs can be long running, on the order of minutes at times, just depending on how much data there is for a particular seed. And with that in mind, with that long running characteristic in mind, we've implemented a job lock using Cloud Memory Store. So pub/sub likes to try to redeliver these messages sometimes before we're ready to be done with them, right? So we've used Memory Store as a simple job lock where we write some metadata to Memory Store as the job starts, and then if we get redelivered a message from pub/sub, we can check and ensure that we don't duplicate effort. The last thing I want to call out here is that, again, this all comes back to these resource APIs. We're reading from these resource APIs and writing output to these resource APIs. We're dogfooding all of these resource APIs that we're exposing to our consumers. We see the same surface they do. So that forces us to make sure that surface is coherent and usable. To give you a sense of how much data we've generated, again, 197 billion genotypes. To backfill this, the process itself is meant to be always on, right? As new data arrives, we make new inferences. We had to backfill this in some way, and we did that, again, by dogfooding the process. At a single moment in time, actually during Cloud Next last year, we had a Kubernetes cluster that was using 42,500 virtual CPUs, all on preemptible nodes at one time, 270 terabytes of memory. And when we talk about cost, we were doing this at 1 cent per CPU hour, which means that as we scale this process up, our costs don't go out of control, right? This doesn't become prohibitive. That's all I've got. That's my Twitter handle. We're always happy to talk about what we do and how we do it.